So one thing I love to do is to learn from my students just as much as they learn from me. So sometimes they'll ask me something and I'll be like, I don't know the answer to that. Maybe you could look it up for me. So today's video was inspired by a student who asked me why that complex number representation with the matrix worked. And I gave him the reason that I found online by asking a math professor. And he went and did some research and sent me a different link. So today's video is inspired by my student, where I explain why that complex number representation in the matrix works.
So this is a supplemental lecture to lecture 3-2 on matrix representation of complex numbers. Upon completion of this lecture, students should be able to explain how to use matrix representation to represent complex numbers and how to use matrix representation of complex numbers in their calculator to solve a system of complex equations. So the theory for why we have to do this is because any calculator before TI-89 cannot solve a complex system of equations. That would be TI-83, 84, 86. You cannot put complex numbers in the matrix, and the seesaw function did not exist yet, which is what you can use in 89 or Inspire. So the theory is that if you have a complex number in rectangular form, A plus JB, it can be represented in a matrix as A negative B, BA. So in order to solve a system of equations, you need to make sure that each complex number is written in rectangular form, such as the following: A11 plus JA21X plus A13 plus JA23Y plus B1 plus JB2. Second equation would be A31 plus JA41X plus A33 plus JA43Y plus B3 plus JB4. So now we're going to enter this system of equations in our matrix. And the matrix, thinking about the way that we represent a complex number as shown here, the first two rows are going to be for equation 1, and the second two rows are going to be for equation 2. Looking at the columns, the coefficients on the x term are the first two columns, the coefficients on the y terms are the second two columns, and then the equals the constant are the last two columns. So the first column is A11, A21, A31, A41. The third column is A13, A23, A33, A43. And the fifth column is B1, B2, B3, and B4. The even columns are now the second term negated, so negative A21, and the first term brought down, A11, negative A41, A31. The fourth column is negative A23, A13, negative A43, A33. And the last column is negative B2, B1, negative B4, B3. So then you put this in your calculator and you do second matrix math, reduce row echelon form, and select the matrix. And the solution comes out where this left half will look like an identity matrix. And what you look at is that the first term would be X. So the first two rows represent the value of X. And the second two rows represent the value of Y. So here you're going to see is that X equals C1 plus J C2. You can ignore the last column. And Y equals C3 plus J C4. Okay, so now that we know how to solve a system of complex equations by using the matrix representation, let's look at why does this work. So the way that we show that this works is by finding the parallels or the duals with real number operations. So let's think about the multiplicative identity. 1 times A equals A times 1, which equals A. So this is the real number identity. What would this look like in terms of a matrix? So the matrix identity for this would be an n by n identity matrix, or I sub n, times matrix A is equal to A times I sub n, where A is also an n by n matrix, and the product of a matrix times the identity matrix is A. Similarly, if you have the matrix A times the inverse of A, or the inverse of a matrix A times A, then that's going to give you the n by n identity matrix. Or if you have the inverse of the n by n identity matrix, that's equal to I sub n. So we've now shown that there are duals in the multiplicative identity between the real number and the matrix. What about if in your matrix multiplication you have that m is equal to 0, negative 1, 1, 0? What would m squared be? So what we will find is that m squared is equal to 0, negative 1, 1, 0 times 0, negative 1, 1, 0. So row 1, column 1 would be, row 1, column 2 is 0. Row 2, column 1 is 0. And row 2, column 2 is negative 1. So that is our negative identity matrix. So m squared is equal to negative I. And so thinking about the parallels between this and our real numbers, we know that we don't have a real number that equals negative the identity matrix. In other words, taking this parallel back to the real number space, we would have that a squared equals negative 1. No such real number exists like that, but we do know that we have a complex number that exists like this. So we could say that in this case, if a squared equals negative 1, then a is equal to our complex number j. So in this case, m would be the dual that represents our complex number j as well. So in other words, we would say it corresponds to j in matrix form. So the question becomes, how could I represent the complex number a plus jb in matrix form? So thinking about our identity matrix, and we'll assume this is for a 2 by 2 matrix, then this would be a times the 2 by 2 identity matrix plus b times m, which represents our j. So it would be a times 1001 plus b times m, which is 0, negative 1, 1, 0. And when we add them together, we get a, negative b, ba, which is exactly what we were using to represent our complex number. And this is the matrix representation of a plus jb. Thanks for coming, and hope to see you again.